are usually numerical. For example, this is matrix A. Matrix A is a 3 by 4 matrix. It's called a 3 by 4 matrix because it has 3 rows and 4 columns. If a given matrix has the same number of rows as it does columns, it's called a square matrix. This is matrix B. B is a 2 by 2 square matrix. Square matrices are useful in that you can do specific calculations with them that you're unable to do with other matrices. For example, you can only find the determinant of a square matrix, and you can only find the inverse of a square matrix. Here is matrix C. Matrix C is a 4 by 4 square matrix. So, the next part is matrix addition and subtraction. And this is where you're adding and subtracting two whole matrices. One of the most important things to remember about this is that you need two matrices that are exact same size. Both of these matrices are 3 by 2. If, for example, matrix B was only a 2 by 2, you would be unable to add or subtract either of these since you have an extra row in matrix A that's not part of matrix B. So to set this up, I have two example problems again. I'll go ahead and set up the first one. Here's the first problem set up. It looks fairly straightforward, and it actually is fairly straightforward. With these two matrices, what you do is you add each element of the matrix to the corresponding element of the other matrix. So for example, in the first one, 4 plus 9 is 13, 44, 1, 15, so on and so forth. Now, the second problem is similar to the second problem of scalar subtraction. In this situation, what you would do is you subtract each element from its corresponding element in the other matrix. So what you end up with is -5, -4, 1, 3, -7, and 10. If, for example, you had B minus A, you'd get something different. You just got the exact opposite. With the scalar subtraction, if you ended up switching the order, you'd be able to tell by looking at it what the other answer would be, because all you had to do was switch the signs.
The first thing to recognize is that it's not the way you might think. You don't multiply just term by term. -1 times 3 is -3. This is not the way matrix multiplication is done. The reason it's not done this way is because this kind of multiplication doesn't prove to be very useful. Here's a simple example to illustrate how it is done. We have a matrix with only one row, 3 columns, and a matrix with only one column, 3 rows. A 1 by 3 times a 3 by 1 matrix. And that will give us a 1 by 1 matrix, a matrix with only one number. And we do multiply entries term by term, but in the following way. 3 times 7 plus -1 times 4 plus 2 times 1. Total that all up and we get 19. That's the way this row matrix is multiplied times this column matrix. When we go to larger matrices, it's the same way, just to multiply a row of the left matrix times a column of the right matrix, and do that over and over for every possible row of the left matrix and every possible column of the right matrix. The size requirement is the matrix on the left, the number of rows, and the matrix on the right, the number of columns of it, will determine the size of the product matrix. Here we see the left matrix with 2 rows, the right matrix with 3 columns, and the product matrix will therefore have 2 rows and 3 columns. In order for the multiplication to be possible, the number of columns, 1, 2, 3, of the left matrix has to match the number of rows of the right matrix. When you multiply matrices, you're always multiplying a row of the left matrix times a column of the right matrix. Let's do this 2 by 3 matrix times 3 by 3 matrix and see how it works. To determine what goes in the row 1, column 1 position, we do row 1 of the left matrix times column 1 of the right matrix. Minus 1 times 1 plus 2 times minus 1 plus 7 times 0 is minus 3. The entry in row 1, column 2 is determined by multiplying row 1 of the left matrix times column 2 of the right matrix. Minus 1 times 2 plus 2 times 4 plus 7 times 2 is 20. The 5 in row 1, column 3 is obtained by multiplying row 1 of the left matrix times column 3 of the right matrix in the same fashion. When we come down to the second row of the product matrix, here we're in row 2, column 1, so we're multiplying row 2 of the left matrix times column 1 of the right matrix. Row 2 times column 2 gives us the 28 in this spot, and row 2 times column 3 gives us the 40 in the row 2, column 3 position of the product matrix.
The transpose of an n by m matrix A is an m by n matrix written using this notation here, where we have A with a superscript of capital T, and we say the transpose of matrix A. Again, notice how if the dimensions of matrix A is n by m, the transpose matrix will have the dimensions m by n. And there are several ways to form the transpose of a matrix. One way is to write the rows of matrix A as the columns of the transposed matrix A, or we can write the columns of matrix A as the rows of the transpose of matrix A. We can also express this using this notation here. If we focus on the subscripts here, notice how these elements have row I, column J, and the transposed matrix has row J, column I. Again, we're interchanging the rows and columns. If matrix A is equal to the transpose of matrix A, then we say A is called a symmetric matrix. Let's take a look at two examples of transposing a given matrix. I always like to start with the dimensions. Notice matrix A is a 3 by 2 matrix, so that means the transpose of matrix A will be a 2 by 3 matrix. So what I'm going to do is go through each row in matrix A and make it the corresponding column in the transpose of matrix A. Since row 1 has elements 4, negative 3, column 1 in the transposed matrix will have elements 4 and negative 3. Row 2 has elements 1 and 6, so column 2 will have elements 1 and 6. Column 3 has elements negative 5 and 2, so column 3 will have elements negative 5 and positive 2. We now have the transpose of matrix A. Notice matrix B is a 3 by 3 matrix, so the transpose of matrix B will also be a 3 by 3 matrix. Again, we're going to take the elements in the rows and make them the columns of the transposed matrix. Row 1 has elements 1, 0, negative 2, which means in the transposed matrix, column 1 will have elements 1, 0, negative 2. Row 2 has elements 3, 4, negative 1. This will form column 2 in the transposed matrix. Row 3 forms column 3 in the transposed matrix. So negative 5, negative 1, and positive 7. So just to emphasize this, notice how row 1 became column 1, row 2 became column 2, and row 3 became column 3. And the same thing for our first example. Row 1, column 1, row 2, column 2, and row 3, column 3. So if this is our matrix A, then we can say the determinant of matrix A, which can be written like this, is equal to negative 8 times 1, that's negative 8, minus negative 3 times 9, which is negative 27. So this is negative 8 plus 27, which equals 19. So for matrix B, the determinant of B can be written like this or like this. And this is equal to 7 times 4, which is 28, minus 9 times 2, which is 18. So the determinant of matrix B is equal to 10. So it's pretty straightforward for a 2 by 2. Now there's two methods to calculate the determinant of a 3 by 3. Method 1 is called the diagonal method. And this is how it works. We first start by copying the 3 columns of the matrix, and then we add column 1 and column 2 to the end to make a total of 5 columns. So again, the first 3 columns are from the original matrix, and then we recopy column 1 and column 2. Once we have it set up in this fashion, we can calculate the determinant of matrix A as follows. Determinant A is equal to the sum of the products of the red diagonals that start at the top and move to the right, minus sum of the product of the green diagonals which start at the top right and move to the left. So we have the quantity of AEI plus BFG plus CDH minus the quantity of CEG, AFH, and BDI. Let's go ahead and give this a try. So if we want to find the determinant of matrix A, we'll first copy these first 3 columns, and then we'll copy the first 2 columns again. So negative 2, negative 1, 2, and then 2, 1, 0. And we're going to have the sum of 3 products minus the sum of 3 products. The first 3 products will start at the top and move to the right. So we have 1, 2, 3. Let's go ahead and find those products. So we have negative 1 times negative 1, that's positive 2, plus 2 times 3 times 2, that's 12, plus negative 3 times negative 1 times 0 is 0. And now we'll form the other diagonals that start at the top and move to the left. So we have 1, 2, 3. So let's go ahead and find those products. We have negative 3 times 1 times 2, that's negative 6, plus negative 2 times 3 times 0, that's 0, plus 2 times negative 1 times negative 1, that's positive 2. It looks like we have 14 minus negative 4, which is equal to 18. The determinant of matrix A is equal to 18.
In this checkpoint, we're going to try to find the determinant of a 4 by 4 matrix. Here I've already put my matrix into my determinant form here with my bars on the outside. Now remember, we can find the determinant using any of our columns. Obviously, I'm going to choose column 3 because 3 of my entries are zeros. So, all I really need to do is start with this guy here, which is 5. But before I start, let's look at which entry of our matrix this is. Since we are in row 2, column 3, this is entry A sub 2, 3. These are odd when you add those together. Therefore, my determinant is going to start with a negative 5 out in front. If I cross out my column and my row, I'm going to then try to find the determinant of 0, 4, negative 3, 1, negative 2, 6, and 3, 0, 1. Okay? So I've reduced my problem to something a little smaller. Now I need to find the determinant of this thing. Well, again, I'm going to go ahead and choose column 1 since I have a 0 entry. So let's start this thing. I don't need to worry about this first entry 0 since 0 times anything is 0. So we'll just move down to 1. Put big parentheses here. I know this must start negative. So negative 1 times, let's see, times the determinant of 4, negative 3, 0, 1. And finally, plus 3, crossing out, I get times the determinant of 4, negative 3, negative 2, 6. Now I need to put that all together. I'll simplify a little bit. I've got my negative 5 out in front. When I go ahead and find the determinant, this determinant here is actually 4, so I get a negative 4. This determinant here turns out to be 18, so I get 3 times 18, which is 54. Simplifying, negative 5 times 50 gives me a negative 250. So the determinant of this big 4 by 4 matrix is the number negative 250. So the important thing to remember here is that you can expand the determinant around any of the columns. You might want to choose the one with the most zeros.